your test on Monday, I think you guys have received the mail and then replied so that you can have a test on Monday around 4:30. So that's what the coordinator told me to inform you. So it will not be a tough test, but it will be a test of how you understood the course and how you can proceed from there. So, okay, so I am just continuing this, what I started in the last Monday class. So basically the topic is same, only now I'll show you some applications, and before that I need to tell you about the technique, otherwise you will not be able to understand what is the application, because this is a different technique than microscopy. I told that it is not the real space image that you are actually seeing visually, but it is a profile or image that you see in reciprocal space, which is we called momentum space. And that is why it is very important to understand the profiles or the images so that you can extract the real space image. Otherwise, you will not be able to understand. So that is my point, and then I'll try to explain those things, and then I'll show you some applications where you can actually see that how these X-ray and neutron scattering techniques are being used to understand the biomaterials or biomembranes or something like that. So let us continue from that with some recap. So I told you that we have delta and beta, because 1 minus delta plus I beta is my refractive index n. So in normal cases, in light reflectivity, light while reflecting, we always see a refractive index, which is for glass commonly we know 1.5. But for X-ray regime, this n is actually 1, like light for vacuum or air, and then for any material it is slightly less than 1, and that slightly less than 1, slightly less than term we denote by delta, and that delta is for X-ray expression is the X-ray expression is basically R0 lab times lambda square by 2 pi times rho electrons. So basically the material has more electron density. That means the material having more Z value, which is basically the atomic number, will have a more delta. So basically the material which is higher Z will have lower refractive index, and the material which is lower Z will have higher refractive index. So this is a completely opposite convention that we can see for light. The light glass has higher refractive index than vacuum, and even we can develop some polymers or some other materials where we have refractive index higher than the material of original glass. So this doesn't depend on the material density, but here it is really dependent on the Z values, that is the electron density, not actually the material density, but actually the electron density. So the higher atomic number elements will have higher electron density, and then we can have higher delta. So the material will be much rarer. That means denser and rarer for X-ray. And for neutron, it is the same kind of expression, but instead of, I told you that instead of X-ray, you have to multiply with R0, whereas in neutron, BI is a different, it's a scattering length, itself is a scattering length. So basically you can think of that this R0 times rho electron is equivalent to Bi in the case of neutron. So basically, instead of R0 times rho electron, if you multiply with Bi, then you can actually you can calculate the scattering length or the scattering function for the neutrons of the same material. So this way we can calculate, and both I said delta X and delta N both are of the order of 10⁻⁶. So this was just a recap of the first day lecture. And then I did the same thing. I guess I told you these things, that suppose I have a body-centered cubic crystal like or space-centered cubic crystal like gold or BCC like iron or cadmium things. Then I can calculate the rho electron by this process, and then I can also calculate the scattering length density for the neutron by this calculation. So these are very simple method of calculation, and then you can have delta and beta easily of material. So this is another system that I told you, that we have a stearic acid which is a soft material, soft material. And then we can think of it is a 20 angstrom and length of 24 angstrom. Yeah, then we can calculate the scattering length density, which is coming out for like 0.33 electrons per angstrom cube. Whereas for, if you see this gold, this is coming out 4.687 per angstrom cube. So you can understand that when the material having Z values, material having values of elements which have lower Z values, like this kind of materials, then we have lower electron density. Whereas when you have higher Z values like 79 for gold, then we have electron density. So this is a kind of a example, and then you can do the similar thing for this molecule for neutron, and you can see that these numbers are actually minus 0.265, and whereas if you replace it by just by H with D, the same material can have higher scattering density. So the convention is that higher scattering density or so getting some noise. Hello, Pavitro. Hello. Okay, so so this is a material having higher scattering density will scatter much more than the scattering material having lower scattering density or electron density will scatter less. So if you put an item which is having higher scattering density or higher electron density, you will get more scattered intensity. Whereas if you have the lower scattering density and the lower electron density, scattering will be less. So that's the convention. And then I will come to this slide, which is not discussed. So basically, what I already told you, that we have an incident radiation that is coming. So this is kind of like a material which is called specimen or substrate or whatever you can say. Then you have a specimen. So this is the interface, and then vacuum is this part, and your material is this part. So incident radiation is coming from the vacuum or air. Vacuum means I don't need to be vacuum. I only can say it is air. So air scattering density is almost zero, so you can assume that it is vacuum. So incident radiation is coming from the source, and then it is reflected from the interface. So you have a reflected portion, and then you have a refracted or transmitted portion. So basically, these two fractions will be observable, and then you can collect either this or this depending on your situation. So in case of, this is nothing new, this is the same as like our glass, that if you have a glass and then your visible light is coming on from top, from the air, and then it is getting reflected, and also a portion of this will be getting transmitted. So for this case, I said the delta vacuum is 0, so n is equal to 1 for vacuum, but for specimen it is 10 to the power minus 6, so it will be little less than 1. So always this will be my denser medium and this specimen will be my rarer medium. And when light comes from denser medium to the rarer medium, you always see total external reflection. And that's the common thing is mirage, right? You know that in deserts we see mirage, and that is very common. And that kind of thing is actually visible for X-ray. So you can have a total external reflection below certain angle, and that angle we call critical angle of total reflection, which is called theta c. So basically cos theta c, cos theta 1, how we define? I define that at theta c, this angle will be like this. So your theta 2 will be 0 and this will be your theta c. So in N2, N1, basically in refractive index is basically in a ratio of sine theta by sine theta 1, sine theta 1 by sine theta 2. But you must remember this thing that in normal cases we calculate the angle from the vertical direction. So basically our angle is this one and this one, but instead in this case we are calculating this thing horizontally. So instead of sine function, now it is basically cos function. So cos theta c is equal to cos theta 1 is equal to N2. So you can, if you do this thing little calculation, so you can expand 1 minus theta c square by 2. And this way N2 is equal to 1 minus delta 2, delta, which is delta. So you can compare, you can terminate the higher order term, and then you can see that theta c is equal to root over 2 delta. There's 1 from both sides cut, and then minus theta c square by 2. Here you have delta minus delta. So delta will be, theta c will be root over 2 delta. So theta c, which is the critical angle for total reflection, so that is dependent on delta, and delta is dependent on low electron or scattering density. So basically the higher electron density will have higher theta c, or a higher scattering density will have higher theta c. So what it will appear in the profile, it will appear that you will have, so this is the normalized reflectivity. We call reflectivity is basically the ratio of incident beam, scattered beam to the incident beam. So when you have total external reflection, then the whole beam, incident beam is being scattered. So if you have whole incident beam is being scattered, then basically you will have a scattered beam is the same as the incident beam, so you will have ratio will be 1. So that's why 10 to the power 0 is 1. So basically instead of having drop, you will have a straight line and up to theta c, and then it will fall like this. So that fall will dictate the same material property, but that is I'm going to talk about. But the point here is to be noted is that you have a theta c, and up to theta c, the material is basically the reflectivity is flat, and then you have suddenly drop of this thing. Okay, so this is one point, and then second point is that QZS is equal to you don't need to go through this calculation, because it may feel boring, or because of you don't, unless you really want to analyze the reflectivity profiles or the scattering profiles, you don't need to do this calculation. What I wanted to mention is, because this is a standard convention, so I am showing all these things. But unless you really need to do this analysis, you don't need to do these calculations. So what you have, sorry, yeah, some of this, yeah. So what you have is the reflectivity, and then you can see that this is a real experimental data. Okay. So you can see that this is a real experiment measured data where you have a thick substrate, basically which we call substrate, which is basically a silicon or something. And on top of, what is the system? On top of, we have a thin film. So basically 1 is my thin film and 2 is the substrate. So substrate is quite thick, that basically if the beam comes from here, it goes into this one, then it gets reflected from one, and then it's coming out from this thing. So complete thing, and then a portion also goes in, but that doesn't come out because it's a infinite thickness. Infinite thickness means infinite with respect to the transmission of the X-ray through the medium, or X-ray or neutron through the medium. So you really don't need to consider the scattering, that basically the beam coming out from this interface, because it is infinite. It is nothing is coming out from this interface. But what is coming out? The beam is coming out from this top surface. Beam is going to the medium 1. Then it is coming out from this interface, 1 to 2 interface. And then it is going out. So basically you are seeing the interference between this beam and the beam coming out from the interface 1 and 2. So it is like the same as you read in your BSc classes, that 2D sine theta is equal to n lambda. So that means that you have a lattice here. You have a lattice here. Your first beam is reflected from here, and the second beam is reflected from here. And you are seeing the interference between these two. So similar to that, we can do these calculations, which you don't need to do at this moment. We just can do. I can say that we can do these calculations. And what the information you can get? Information is that you can get the film thickness. So you have a very nice oscillations. And from these oscillations, we can calculate the delta QZ. So this is plotted with respect to QZ, that expression I showed you in last class. So you can calculate the delta QZ, basically the difference between this dip to this dip. And that dip, with respect, you can calculate d is equal to 2 pi over delta QZ. And then you can say that this is my thickness of the polymer, this thickness of the film. So it can tell you the thickness, it can tell you the electron density, because you have a QC information here. And QC information, you can, from this QC information, you can talk about the density of the material. So if it is a simple film, it's like a polymer film or any biofilm or something. So I will show you those examples. So you can see that you can measure the density of the film. You can measure the thickness of that film. And on top of that, if I have not considered here that I have only considered that this is a smooth interface. That means it's a sharp interface where beam is coming from here and reflected from here. So it is a sharp interface. So, but the real thing is not the sharp interface. If you see, this is a QZ to the power 4. QZ to the power minus 4 is the 4. So if in real case, it is not the QZ to the power minus 4 exactly, but it is a little different. And that difference is because that your surface is not exactly flat, what you are seeing, what you are looking at, but it is actually a little rough surface. So suppose, okay, let me go tell one moment what is the rough surface. So rough surface is something like this, where you have this roughness. This roughness cannot be seen by naked eye, but you can see this thing in AFM or ACM or PEM, this kind of pictures you have seen that. So what is it's in the length scale of Armstrong. And Armstrong length scale means you cannot see it in the visible light or in the microscope. You need some electron beam or some other rays to see these roughness. So what I am talking, what I am trying to say here, here the important point is that you don't have to do this calculation, but you can actually extract the density, you can extract the film thickness, and also you can extract the roughness of the interface. So these are three major informations that you can extract from a refractive. So if you have a thin film, which is not so rough, you can do an X-ray reflectivity measurement. And from that measurement, you can actually extract the film thickness, film density, and the film roughness. So these are the three major things you can talk about your film, and that you are not easily available, that these informations are not easily available in any other techniques. And that's basically the advantage of X-ray or neutron reflectivity for your system. And I'll show you those applications, then you can understand better that how these these techniques are being used to understand the material. But instead of one single surface, you can have a multiple materials. And actually, in real system, we have this kind of graded surface. So you can have a thick density, thick layer, thin layer of different materials, and you can have then a complicated reflectivity profile. But this reflectivity profile can be analyzed, and then you can extract the information of all the individual layers. So just remember it that you are actually not seeing a single layer, but you are seeing multiple layers of, and you are getting the information about thickness, roughness, and density of each layers. So that is the very unique thing for X-ray or neutron reflectivity, because you are not seeing only the surface topology or the surface information, but you are actually looking what you can see by cutting TEM or kind of thing, but it is a much more non-destructive way and much more precise measurement, where you are not destroying your sample, you are not disturbing your sample, but you are actually measuring all the informations along the depth. So particularly I say along the depth. What it is mean? It means that you have a density variation along the depth, and each layer of density variation you can extract, and depending on your reflectivity profile, and then you can say that this is my material along the material information along the depth. So that's why I said in the first day that your geometry of measurement is important. So for doing a measurement on your sample and get the information along the density variation along the depth, you need to do a X-ray reflectivity or neutron reflectivity. So that is the key point of my talk, that to get the information about the sample along the depth, you need to do X-ray or neutron reflectivity. Okay, so, and it is obviously it is not a ready-made information that you can see in microscope, but you get a reflectivity profile like this, and when you get a reflectivity profile like this, you have to analyze, and then you can extract all the information. For doing this analysis, you need to go through all these calculations, which is little beyond the scope of this lecture, because it needs a elaborate lecture series and calculation. Okay, so here important thing is that layer less dense than the substrate, layer denser than the substrate. So if substrate means, suppose we have deposited some film on silicon substrate. Most common cases we use silicon or quartz or glass substrate, something like that. But I told you that we need to have a substrate, or we need to have a film whose thickness is comparable to X-ray regime. That means I can measure something like because my resolution, here the resolution comes in, because I told you my some of this picture is not coming here. Yeah. So I told you that D is equal to 2 pi over delta QZ. So delta QZ is basically the difference between these two dips. So now if these two dips are too close that you cannot distinguish, then you cannot measure D. So that's my resolution. Basically, and that resolution is something like 100 nanometer or 200 nanometer. So basically, you can measure from the sub-nanometer range to 200 nanometer. It's a huge range, huge dynamic range of measurements, 200, 300, maybe 500 nanometer. If you have sufficient resolution of your instrument, you can do that. So this kind of measurements can be done using X-ray reflectivity. And then here I try to point out the one point that if you have a single surface, that is the substrate, then you will have a reflectivity profile like this, so which is a blue curve. And then if your sample is higher thickness than the substrate, then you will have this kind of reflectivity profile, which is basically the bottom of your these peaks. So basically the dips are basically the convolution of the substrate. Okay, and if you have a thinner, rarer medium than the substrate, basically suppose what rarer or denser means, suppose I have deposited gold on silicon or quartz or glass, then gold has much higher density than the glass or quartz. So that means the gold will be on top, and that convolution, the bottom deep of these peaks will have the convolution of the substrate. So you are actually measuring this one, but actually your substrate profile is this. And from that, you can immediately define immediately extract the substrate roughness, and you can put, and this can be analyzed. But if you have a let's say some lipid film or some steric fatty acid film, which is soft, which is having basically the carbon, hydrogen, nitrogen constituents, and then it will have a density lesser than the silicon or glass. So then the density means electron density. Okay, it's not the mass density, it's the electron density. So you will have a dense, lesser medium like lipids and everything. And then your peaks will have the convolution of your substrate reflectivity. So this kind of analysis is a quick thing to define your film properties. And from these oscillations, you can actually determine the thickness and the density and the roughness, all these informations. So I talked about delta. I didn't talk about beta because beta is the absorption. I said that the imaginary part, which is the coefficient of I. So I said the refractive index is actually N1 plus I N2, or N prime plus I N prime. So that means it has a real part, which is N1 or N prime, and the imaginary part, which is n double prime or n2. So I is the, in physics and in reality, the imaginary part is associated with the absorption of the material. So the delta is the real refractive index that you can see or you can measure, and beta is related to the absorption of the material. So the more beta, you will not have this sharp fall at the QC. You will have this kind of convolution, whereas you have a less beta, you will have like this. So ideal case, it will be like goes like this and then fall like this. But in reality, you will have this kind of bending at the knee. You can say the knee, and then you have more beta. The bending is much smaller, and then you have a curvature is much larger. So you will have a this kind of fall. So the material having less absorption will go like this. Material having more absorption will go like this. And all these informations you can extract from your reflectivity profile. So that means you can talk about your materials absorption properties. You can talk about your material's thickness. You can talk about material density, and you can talk about the material roughness. Okay, so this is the thing that I already talked about that. And this is the real experiment. So how it looks like. And you can see that you have this kind of film, then you have 10 Armstrong roughness. This is sigma is related to, basically denotes the roughness. So if you have a roughness of 10 Armstrong, 10 Armstrong means 1 nanometer, and for lambda measurement was done at 1.54, then it will go like this, and then you can have different measurement. But so you can actually measure reflectivity from water surface. So something like water surface, you can see that how powerful this technique is. So you have a water layer, and then on that water layer, you can measure the reflectivity. Okay, so this is a real measurement to show you how we can do that. So the system is basically a silicon substrate. On top of, you have a silicon oxide layer, which basically it's a oxidized silicon surface. So don't think that silicon is up to here and silicon oxide starts here. It is basically the electron density curve or delta curve. So basically the film is a silicon, then silicon oxide, and the polystyrene film. PS is for polystyrene polymer film. So you have a different electron density. So that's why this silicon is 0.71 or 0.7. So this is here, then it's something like 0.56, and then it's 0.33 or 0.34. So 32. So this kind of reflectivity from this analysis, you can extract this kind of information. And the main thing is that you get in real measurement in the experiment, you get this kind of reflectivity profile. So you get this kind of profile, and while you do the analysis, you can extract this profile, this solid line basically. And from that solid line, you can infer that this is my silicon substrate, this is my silicon oxide grown on top of silicon, and this is my polymer film. And then you can see that this is a little convoluted because it doesn't have a sharp interface. So from that sharp interface is, so this convolution actually denotes the roughness. And this convolution, you can see that it is a little longer, and this roughness is more. So you can say that you can actually say how much roughness is this one, and you can say how much roughness is this one or this one, and then you can talk about the density. You can say that this is my thickness, this is my silicon oxide thickness, this is my polystyrene thickness, and this is my density, and this is my roughness. So the whole film whole film, and along the depth of the film, you are actually telling this thing in your from the reflectivity profile. So that's the main point. And then I am going to talk about some applications. So these are some applications may excite you something. So this is so basically now last half an hour I will be talking about this application. Okay, so I already told you these are stearic acid molecules. So these are actually amphiphilic in nature. Amphiphilic means you are biology student, so you know what is amphiphilic better than me. So it is basically you have a hydrophobic part and then you have a hydrophilic part. So we call it the hydrophilic part, we call it head, and then the hydrophobic part, we call it tail. So basically, why it is tail? Because if you made a vesicle, then basically all heads basically form the vesicle, and that it can have tail projected out, or it can have head on the top and tails can go inside depending on the environment. So that the micelle convention, and if these molecules forms vesicle underwater, then the head part will be outside and it will be facing the water surface, not water surface, but basically in the water molecules, and the tail part, which is hydrophobic part, it will go in the vesicle, inside of the vesicle. So that's the minimum energy configuration. So that's called the micellar form of this kind of molecules. So we call it tail and this kind of head. And this is instead of forming it micelle, what we have done is that we spread it on water surface. So when we spread it on water surface, spread means we made a solution of these molecules in chloroform, and then we drop by drop, we basically fill it on water surface. So this is a kind of oil. Okay, so it is like your all oil, but in these oils, the chain of the oil molecules is small, and that how small it is something like 1 to 2 nanometer or 3 nanometer. So it is a chain of 1 to 2 nanometer oil, and when you spread it on water surface, then basically it forms a monolayer. So these are the basic thing, and then this monolayer is called the Langmuir monolayer. So how it goes in there? So basically you have a head part here and the tail project out, and then you can form a monolayer of molecules. So this is the similar thing you see in Neutron's ring. Neutron's ring, probably remember that if you spread some oil, put a drop of oil on water surface, it basically shows you some colors, some red, green, blue colors. Because of oil reflects that, because oil stays on the water surface, it cannot dissolve into water surface, so it stays on water surface, and basically it reflects the light. Light means visible light, and the thickness of those oil chains are of the order of micron, and so it reflects the visible light and you see those red, green, blue colors. So that's called Newton's ring. So because Newton's observed this thing first and then he gave this explanation. So it is but here the chain length is small. Chain length is 1 to 2 nanometer, and in your real oil that you can drop, basically vegetable oil or this mustard oil or this kind of thing, that is in the range of micron. So that's why you can see it through visible light. But if you drop this thing on water surface, you will not see anything on with the visible light. But it is actually forming monolayer, And this kind of monolayer, we call it Langmuir. The advantage of this thing is that this is the acid part, COOH. So basically it's OO, and then you have a H. So if it's a stearic acid, then you have a 18 chain, and then you have a H hydrogen bond here. So then if you put it on water, then hydrogen basically dissociates, and then you can put, if you have some metal ions in the dissolved in this water bath, then that metal can get attached, and you can have a metal bonding in this basically in this part of the molecule. So you spreaded stearic acid or arachidic acid or palmitic acid, so some acid with H, and you have some metal ions in the dissolved in the surface. We call it water surface, and then that ions get attached. So you can have a molecule with a single metal attachment. Now what is the advantage of this thing? That you have a monolayer of molecules. So you have a stack of molecules like this, and with an attachment of a single metal. And depending on the valency of that metal, you can attach single tail or double tail or triple tail. So you can form a metal and organic layer. And then you can deposit it on the substrate. So this is my silicon substrate, and you can deposit this monolayer on this substrate. And that is what I am going to show you, that how you can determine the structure and the organization of those molecules from the from this monolayer. So the deposition process is very simple, that you create a monolayer on water surface, and then you basically dip the silicon substrate or glass substrate. And depending on the nature of your substrate, either the hydrophilic part gets attached or the hydrophobic part gets attached. So basically this is the convention, and then you can deposit multiple layers or you can deposit single layer. So if you go through the monolayer single times, you have one layer deposited. If you go 2 times, you have 2 layers deposited. So this way you can actually deposit layer by layer deposition. And that's the advantage of this Langmuir-Blodgett deposition technique. So instead of a single vesicle or multi-layer vesicle, you can have a single layer of molecules on your substrate. And that technique we call Langmuir-Blodgett technique. And then what we did, we actually measured the neutron and X-ray reflectivity. So on the same matrix, basically same sample. So we measured X-ray reflectivity in our laboratory, and we have measured the neutron reflectivity in neutron source, because laboratory neutron source are not available, because neutron source is a dangerous thing. So you have a neutron reactor or spallation source, so where you can do these measurements. And we have done the neutron measurement, reflectivity measurement, and as well as the X-ray reflectivity measurement of the same sample. But here the advantage is that because it is the same sample, so one case, it is basically the scattering length of that element is getting multiplied to give you neutron reflectivity. And another case, the electron density multiplied with R0 will give you the X-ray reflectivity. So the material density remains same, material mass density remains same, only if you multiply it with the scattering length density for neutron, then you get neutron reflectivity. And if you multiply with the electron density of the material, then you get the X-ray reflectivity. So we basically analyzed both X-ray and neutron reflectivity. Now this is a this is a real experiment I am talking about, published paper. So you can see the reflectivity. So this is a single layer reflectivity from of this molecule. So you can actually talk about the length. So this T for this part. So you can say that this is something like 20 angstrom long length, and then you have a head part, which is this tiny part, and then you have a silicon substrate. So you are actually determine the structure of the film, such a thin film, 2 nanometer, 20 angstrom means 2 nanometers. So 2 nanometer thick film, the structure of a 2 nanometer thick film, without destroying the surface, without destroying the sample, you can actually measure it. And then you can say that one head group is attached to two tails. So not only the single, because this is done with cadmium. So this cadmium is a bivalent molecule. So it's supposed to get attached to molecules, and that is what exactly we are getting here. So you can say how you know this cadmium, because of the density. You can calculate the density of the material, and then from that density of the material, you can say that it is cadmium. So this is a double layer, and this is a triple layer. So you can see that, sorry. This is both are triple layer, 3-layer deposition. And here, what we have done, I told you that isotopic substitution in my last class, that you can actually change the H by D. H means hydrogen by deuterium. So if you do this isotopic substitution, then for X-ray, it doesn't change the density, because X-ray electron density will remain almost the same, because the electron number is not changing. It is the deuterate is basically one neutron is getting added. So your electron number is not changing. So your electron density is not changing. So your X-ray reflectivity, if you replace this hydrogen by deuterium, your X-ray reflectivity will not change, but your deuterate, because of deuteration, your neutron reflectivity will change. So that's what exactly we found, and we can see that this is my neutron reflectivity, and this is my, so you can see that in X-ray reflectivity, H means head part. This is not hydrogen. This is the head part, is basically the higher density because of cadmium. So this is my cadmium part. So you have higher density, and this is my lower density part, is basically the hydrocarbon chain, CH2 chains. So this is my hydrocarbon chains, and this is my head group, again cadmium, and this is silicon oxide silicon. So this is the configuration. So you can talk about that this is my configuration. So head, tail, head, tail, this kind of configuration exists in the film. But in this case, what you can see that it is the same thing, same film. When you do this reflectivity, neutron reflectivity, you can see that this tail in one case is higher density and one case it is lower density. Here it is hydrogen head part is higher density, and here head part is lower density. Why it is that? Because this was done without deuteration. That means without isotopic substitution. So this was without isotopic substitution, and this was with isotopic substitution. And you can see that this is the electron density profile, or the scattering density profile, that is being changed. But your mass density profile will remain same for both the film, because mass density is not changing. It is the electron density or the scattering density is changing because of the deuteration. And that is giving you the unique solution. So you can have a multiple solution, because it's not a real image. No? It's a reciprocal space, some profile. And you can fit it with multiple profile. But multiple this kind of profile. So your solution is not unique, but doing this thing, you can actually uniquely converge to a solution and to predict your system. So this is the one of the biggest advantage of doing multiple simultaneous measurement of X-ray and neutron. And that is what we have done. And this was published in long back, but it gives you some indication that how you are measuring this thing. So this is the this is more of a details, so I am not going into that. So this is published in 2001, but it is basically the summary of the whole measurement. So here you have a neutron reflectivity and this X-ray reflectivity both simultaneously. And then we have then done 1, 2, 3 layer. I told you that you can do layer by layer deposition. So you have 1, 2 nanometer, 4 nanometer and 6 nanometer kind of thing, some kind of film on your substrate. And the same film we measured neutron reflectivity, and then we can uniquely converge to an idea that how these molecules are actually assembling, how they are reorganizing among themselves after deposition. So those kind of all the detailed information you can talk, and these informations are very rare from other techniques. So basically, this is the observation that you this different color means that you have a deuteration. So these are deuterated molecules, where these are not deuterated, hydrogenated molecule. So even if you deposit first layer, if you have a hydrogenated molecule, second layer deuterated, so you can actually have a reassembly or reorganization on the surface of the film, and that is exactly coming out from this. So next, I will be talking about some model membrane. So these are kind of new kind of these. The one I showed you is a little old study, 2001. So which is quite old study. But now these are quite new studies, but these are on biomembranes or bio. So what we have done here, that we can create a membrane of lipid molecules. So this is not the exactly cell biology that we do, that you people do or other people do with a real cell molecules or real cell membrane or this kind of thing. But this was done with a specific molecule. So let's see how DPPC is interacting with this molecule, how DPPE is interacting, or how DPPS is interacting with this molecule. So it's not a real cell environment, but it's trying to understand the specific interaction mechanism of a lipid molecule with the protein or cholesterol or hemine. So this kind of thing. So what we have done here, we have chosen 3 molecules. You can think of one is like a polymer chain, which is actually a protein of spectrin. So you know this spectrin is a membrane protein. It's basically it forms the cytoskeleton of a cell. So we took this spectrin, which is similar to a long polymer chain. Then we took a cholesterol molecule, which is basically a kind. You can assume that this is a kind of cylinder. And then we have a planar molecule like a heme. So these are the 3 systems that we have incorporated in a specific molecular lipid membrane. So in that way, we can talk about the arrangement of the molecules. We can talk about the interaction, specific interaction or specific adhesion with the head, with the tail, or its head or tail means with the DP part or the PC part or the PE part or the PS part. So this kind of thing. And on top of that, when you create a membrane, then basically you have the problem that your membrane in previous slide, what I was showing you, this stearic acid or this cadmium stearate or this thing, lipid fatty acid molecules, then this once these molecules attach to the substrate, it fixed. It cannot basically percolate or it cannot reorient themselves to other layers. So that's why we took two systems. Two is call it soft membrane. Soft means soft membrane on soft surfaces. Soft surface means one case is it's water. So water means that it can move or it can reorganize. And another case, it's a brush-like polymer. So in this case, it is actually forming a layer, a membrane layer on top of a brush, polymer brush, so that it can reorganize or reorient within after deposition, depending on the environmental change. So that these are the two basically the membrane system that we have chosen. And these are the molecules we want to see how these molecules are interacting with this membrane. So this is our motive. So that's what we have done. And then we have done laboratory-based measurements and the synchrotron or X-ray scattering or neutron scattering measurements. So here I am showing you some X-ray scattering measurement. We also have done neutron reflectivity measurements, but that I am not showing it here right now because it can only complicate your image. So what we have done here, we have deposited the polymer layer. And then we have, so this is the surface topology of the polymer. So basically, this you can see it's a little bit rough. But once you other important thing is that, so here that you can see that in this case, the head part, that means the hydrophilic part is on the water and the hydrophobic part is in the air. So that's the minimum energy configuration because it's stable. This monolayer is stable because it has a hydrophobic part and air is hydrophobic. So basically it can stable only in this form. But here, this part is water. Okay. So when you feel this is like a cell, complete, it's a experimental cell. So experimental cell basically, so you filled it in water. So that means hydrophobic part of this thing cannot be here. This membrane cannot terminate with the hydrophobic part on top, but it can terminate with the hydrophilic part on top and the hydrophobic part in the middle. So basically, you can think of that this is a single layer vesicle on a substrate. So basically, instead of having it in a curvature, or it's in a vesicle form, it is a planar form of a vesicle, part of a vesicle. And then you have a inner part, you have a hydrophilic part, which is the PC or PE or PS. And this part is basically DP or DM or DA, DP, DS, or this kind of audio, all these kind of hydrophobic part is here. And again, on top of you have a hydrophilic part, which is PC, PA, PS, or PE, whatever you want. So here you have a basically bilayer, and here you have a. So here you have, we call it lipid bilayer, and this one we call lipid monolayer. So what we have done, we have done that. We have taken DMPC and DMPE, these two lipid molecules, and then added spectrins. So when we add spectrins, then we can see that this is the okay. I'm just mentioning it. I'm not going into details. So this is called a phase diagram. Phase diagram for we measure the surface pressure on versus molecular area. So this will dictate, show you that when spectrin, you add spectrin to the monolayer, then you have this extra area. That means spectrins are getting attached to this monolayer. So because of spectrin attachment, this area increases, and that increase is basically shows you that there is a spectrin attachment to the DMPC monolayer, and here it's a DMPE monolayer. And from that, how it is that how this is different from the pristine. So you can talk about a lot of things, but I am not telling you those things because it is not the purpose. Purpose is basically now you can what we have done, that we have deposited those, we have prepared those bilayer films and then added spectrin, and you can see that you don't need to think about this part. This is the fitting, and then you can think about this model, that this is my silicon oxide here, and then you have a polymer brass layer something here, and then you have a head part, then tail part, and then again head part, and then you have a spectrin molecules here. So what it means, that spectrin molecules are forming a layer, kind of a skeleton on the DMPC bilayer. So in real cell, we have a lot of PC molecule. So we have a lot of PC molecules in real cell. So when there is a bilayer of PC molecules, because cell membrane is a bilayer, then spectrin forms a cytoskeleton of uniform layer like this. But when you have a PE molecule, then basically it doesn't form. So this is the top surface. So this is the water surface that I was talking about. So when you have a PE molecule, then you don't see this kind of spectrin layer on top of PE. So that means in a cell, you can actually now go back to your cell biology and can say that when you have a PE molecule, then the cytoskeleton, that uniform layer, doesn't form. And that actually give you a hint that how this in your cell, and there is a so there, if there is an important molecule which needs to go into the cell, or there is a waste that needs to go out of the cell, then actually in the membrane, which consists of PC and PE molecule, also there are other molecules too. So they actually reorganize, the membrane molecules reorganize, and then they form a PC packed region or PE packed region. And then when you have a PE packed region, then the membrane, the cytoskeleton actually breaks. And because of that breaking, then the molecule from outside can come in, or molecule from inside can go out. So this way cell transportation can be modeled or can be talked about from this kind of measurements. So these are kind of very good information which you are actually able to talk from this X-ray and neutron reflectivity. And here I am showing just the X-ray reflectivity results to show those kind of things. So these are finer details, that when you have a bilayer kind of thing, when you have a PC molecules, it forms a layer on top of it. But when you have a PE molecules, then you don't see this kind of layer. And that means that cytoskeleton doesn't form here, and then the molecules can come in or go out. So this is a kind of another study that I'm kind of running out of time. So I'll quickly go over two more study, because I started with the polymer kind of spectrin chain. Then we have a cylindrical cholesterol molecule and the planar hemine molecule. So this is a kind of history, that how cholesterols are getting attached to the membrane and how make it stiff, or these kind of things. So these are all different models that people are talking about, And here we have done that it is on the some monolayer surface, that how we have changed the cholesterol concentration and how this cholesterol concentration actually changing the monolayer. So that was the basically the motive of the study. And we have seen the how monolayer thickness variation is changing and how these cholesterols are getting attached, or how these cholesterol. So what we have seen that if you have a, maybe I can see it go directly here. So this is the membrane that you have a single molecular head and tail of this molecule. Then you have a low concentration, then cholesterol, this head can get tilted and the cholesterol can sneak in to the membrane and can stay like this. So if you have a more kind of cholesterol concentration, there is a at some point there will be a crystallization formation of the formation of the cholesterols, and then it will basically form a crystal on the substrate. And that kind of, so one case it can form a tiny crystal within the membrane, another case it can form a tiny crystal, it can actually dissociate and form a complete stiff. So this stiffness, actually if you measure, you will see that stiffness is much higher from in this monolayer, and that is actually, that is why we see in real blood vessels, like this crystallization formation inside the vessel. So this kind of crystallization formation you can talk about from the model membrane, and you can actually determine that what is the concentration and how this crystallization is forming in the membrane. So this kind of measurements were done using X-ray reflectivity. And then I'm talking about one thing that that is a hemming molecule. So hemming molecule is basically it's a hemoglobin. So hemoglobin, if you take the globin part out, then you have only hemming molecule, which is having, which is a planar molecules with iron inside inside this center of the this rectangular plane. So here we have changed the concentration of this hemming molecule for the PC and P membrane, and what we have, I am not going into details. So basically these are analyzed electron density profile, but you can see that this is a kind of, this deep is changing as a function of concentration. But if you see this one, this deep is changing in the opposite direction. So one case deep is going in lower QZ, another case deep is going to the higher QZ. So that means, so going to the lower QZ means it's a reciprocal space. That means the thickness increases. And going to the higher QZ means the thickness decreases. So the same lipid molecule, DMPE or PC, so you are just changing the head group, basically the E and PC head group, and you can see that how these hemming molecules actually dictate that how the organization of these molecules on the. So here we have a cartoon. So these are the PC molecule, and then when you have a 20% of hemming, then you can have this kind of structure, and then you can see this kind of profile from these things. And when you have a more than 20% of structure, then you can have a kind of this kind of singlet. We call it singlet and doublet and triplet, this kind of arrangement, and that can be. So so far this is the X-ray and neutron reflectivity, because this is only the information about the sample in the out of plane direction. So that's what you are measuring from X-ray or neutron reflectivity. But there are other techniques. There are several other techniques where you can talk about a lot of other things. And I showed my initial diagram that you can talk about diffraction where you are talking about this lattice spacing. You can talk about the nanoparticle size, shape, distribution, and all these things. For that, you need G-SAX measurement. So this is another technique that instead of going along QZ direction, basically in that measurement reflectivity, I had a variation of QZ because my incidence angle is equal to the reflected angle. So I only varied along this direction. But in G-SAX measurement, we can actually vary all the angles and then we get other Q mapping in other directions too. And depending on that, we actually talk about that how these molecules are forming bigger bigger domains and then size, how they are distributed. So all these type of informations you can stock. Here we have a very good example of real measurements that you have a cylindrical rod like this fiber. So these are highly humidity sensing molecule. And if you change the humidity, you can see that the patterns are changing. So what we have done that how this humidity or water molecule goes into the into these vesicle or micellar forms of these fibers, and then how it is changing, and that can be determined by the G-SAX measurements. So this is basically the summary of that, and so at this point I end here, and I basically wait for your comments or any thing that you want to ask or something if you have questions. So what I told you in this whole lecture is that some basic X-ray and neutron scattering techniques. And then I told you about how we can measure the film, or about can measure the thickness, density, or roughness of a composite film or a simple film, and how we can actually determine the in-depth information along the depth information of the sample. So this is this is the aim of these two lectures. I hope you could understand something from this. Okay, so now if you have some questions, you can ask, or I can stop this. Yeah. So seems to me you guys have not understood it properly, or because if you have understood, then you could have some question. I don't know what to say, but probably this is the maximum I can do. Yeah. If you have some doubts or questions, you can ask. Otherwise, I'll just wait for a few minutes and then leave. You can have a couple of questions in your next exam, which is due on Monday, and then Okay, I think we are done. I think we are done. So thank you for your attention. And yeah.
Okay, sir. There are no questions.
Yeah. Goodbye. Bye. Thanks.
Okay, sir. I will close them.
Yeah.